is the questions on moments, and there's a little bit on materials on stress, strain, young modulus. So this first one is on moments, and there are two really difficult situations you can get in moments questions. The vast majority of moments questions are fairly straightforward, and you've got one pivot, you've got an object balanced on that pivot, and you've got forces acting either side, and that's your straightforward seesaw arrangement. The more complicated ones are when you've got more than one pivot. So perhaps you've got two supports on a bridge acting either side, and you've got to work out the size of those support forces. They still work on the same principle. You need to try and turn them into two separate seesaws. More on that probably later this week. And the other one is a question like this, where you've got forces which aren't acting perpendicularly to the distance between the force and the pivot. So with moments, there are two things to remember. You've got the principle of moments, that is, the sum of the clockwise moments must be the same as the sum of the anti-clockwise moments, and the equation, which is the moment of a force, is the size of the force multiplied by the perpendicular distance between that force and the pivot. Now in this question, I'll turn the pointer on. You've got the weight acting on here, and you've got a distance there, d. That's what we're trying to work out. D is at right angles to that weight. That's good. That's absolutely fine. Here, though, the force is acting like that. The distance we have is acting there. Those two things are at right angles to each other. So to work this one out, we need to figure out how much of t, what component of t, is acting vertically at right angles at 0.75. So if I skip on, I've done an answer to this. So we've got this diagram, and the first thing to do is to work out how much of t is acting vertically, and to do that we need to make a triangle. So we've got there. This side is the vertical component, and that is the adjacent side of this angle. The value of t, which is the 5.1 seconds, that is the hypotenuse of the triangle. So we're going to be thinking SOHCAHTOA. This is the adjacent side we work out. So it's K, cos of 40 equals adjacent over hypotenuse. So cos of 40 times by the hypotenuse will give us the length of that side. So our moments calculation will be the clockwise moment, 1.2 times 9.81 to get that mass in grams times by d, equals t cos 40 times by 0.75. We set that into that kind of line there. Rearrange both sides of 0.91 and gives us d. The next one, the stress strain graph. Remember, stress is force over cross-sectional length, and strain is tension over original length. Stress divided by strain, that gives us the young modulus. Units of stress, pascals, and units of strain. That's right, strain has no units at all. You're just doing one length divided by another. So this material is showing a graph which is a straight line and then it stops. And that means this material is brittle. It has no elastic region. This is the elastic deformation. So as we increase the force, it extends proportionally and then it breaks. That point there is the elastic limit. Well, we don't know that actually. That's breaking point. If it was less brittle and it started to behave plastically, then that line would start to curve. So the physical properties of this material are that it's brittle and elastic. It has no plastic region. We know it's elastic because it's a straight line. And I've drawn on here a material which is ductile. See, it has a steeper gradient in a straight line section because that's the larger young modulus. Stress over strain is the modulus. So if stress over strain is the gradient, then bigger young modulus means bigger gradient. And then as it's ductile, it has a hard plastic region. Things are behaving plastically when, if you remove the force, they don't bounce back to how they were before. Elastic materials, when you take away the force, they spring back to how they were. Plastic deformation is permanent deformation. Right, this is a good question. This is the cable car. And there's loads of questions similar to this. There's ones with kind of picture frames hanging from wires. This is a cable car hanging from one cable, but it's making the cable kind of sag where the car's hanging from. So the first part of this, I'm trying to remember which order this went in. I think it must be this. So the stress over the strain is the Young modulus. So to work out the strain, we're given the Young modulus and the stress in the question. So stress over Young modulus, stress strain is 9 times to the minus 5. No units because it's extension over length, meters over meters, and they cancel each other out. Part 3, calculate the weight of the cable car. So this is the tricky one. No tension. I've got the questions here, which is what I was trying to look for, because I can't remember what order this goes in there. So the first part was the strain. It was working out the tension in the cable, and that's this answer here. So the tension in the cable. Right. So this goes from this question to here, and then up. So stress is force over area. The force is the tension. Stress is 8 times 10 to the 7. The area, I'm going to assume these cables are circular, and we know the radius is 2.6 times 10 to the minus 2 meters. Area of a circle is pi r squared. So pi r squared times by the stress of the force, which is 3.8 times 10 to the 4. And then the weight of the cable car. That weight is shared out between the vertical components of tension. So the vertical component of one of these tensions is going to be T times sine of 12. It's going to be the length of that triangle there. T is the hypotenuse. This side here, the vertical component, is the opposite. So it's SOHCAHTOA again. Sine of theta is opposite over adjacent. Opposite over hypotenuse. Sine of 12 is going to be the vertical component divided by T. The vertical component of the tension would be T sine 12. West downwards is going to be equal to 2 of the vertical components. This right hand side plus the vertical component of the left side. The weight of the cable car is going to be equal to 2 times T sine 12. We are told that we've worked out what the force of tension in the cable is up here. So 2 times 3.8 times 10 to the 4 times by sine 12 is this 15,801.3 newtons. Writing that to two significant figures gives us 1.6 times 10 to the 4 newtons. Hopefully that matched up with everything you said. Make sure you're marking those using the mark scheme, using this, make corrections, and going back over some of this work. Assuming this was all good, there are some more questions on this on Google Classroom, so please give those a go, and see you soon.